Let's switch gears now and talk about the various assumptions in regression. It's important to know what these are. There are 4 or 5 of them. And it's important to know that these assumptions need to be met in our data in order to have the most accurate results that we can. Having said that, we are going to be treading into more murky waters than we have been in up till now. That is because for a lot of these assumptions, there is, first of all, a debate as to how to best resolve them, how to best deal with them. And there is some uncertainty as to testing for them such that we know that they're really occurring versus not occurring. So there's some uncertainty in that aspect. And I'll try to elucidate that better as we go along, further clarify what I mean by some of these things. But just know that I think sometimes we assume that the experts have all agreed on what to do in a certain situation and that that's what we're going to do from now on. And in some cases in our field, that is true. For example, we have bootstrapping methods now that we didn't have before. And almost all the experts agree that bootstrapping is a robust way to deal with data that has, for example, normality assumptions violated. So we do have some of those hard and fast things that we can depend on. However, there are other cases where data and I should say knowledge is still emerging on how to best deal with assumption violations. So measurement error in the predictor variables, I think, is one of those where there's a lot of there's still some uncertainty as to how to deal with it, because we know that we have measurement error in all of our variables. We have imperfect measures of our constructs. And so to the extent that that measurement error is impacting the veracity of our results, we really don't know for sure. There is a new paper out that one of my colleagues drew my attention to that I haven't read yet, but it's about this very issue of measurement error and how it impacts, and they argue greatly impacts the inferences we can draw from our regression analyses and also path analyses, which you'll learn next quarter. And this is something that we really can't do much about because our measures are not error-free, and I'm not sure they ever will be. I can't foresee that in the future. So they, I believe, did some Monte Carlo studies and some different simulations and tested different degrees of measurement error and how it impacts the results. And again, I haven't read the study yet, but from what I hear, it can be pretty drastic. And so I don't know what solutions that they give. A lot of times researchers, what I've noticed when writing these types of articles is that they clearly delineate the problem, but they don't have a good solution yet. And maybe you've noticed this when you're reading books about societal problems as well. Typically, we can very clearly articulate problems, and we can articulate solutions way less clearly, and that's fairly normal and just kind of the progression of knowledge. So I could go on and on about this, but suffice it to say that if you feel the uncertainty in this section, that's normal. So I'm going to try to let you know what are the important things to know. And after that, you can go to Field for reference. I highly recommend his chapter called The Beast of Bias, and it is very thorough, and it gives you all kinds of different options to try when assumptions are violated. I'm not going to go over all of those in this lecture because it's just vast, but it's there mainly for your reference in Field. Okay, so the first assumption is that a linear relationship exists between the predictors and the DV, and it's not curvilinear. We're going to be learning how to test for curvilinearity or nonlinearity. That's, again, synonymous terms, later in the course. But for now, we just need to be able to visually look at things and see that the relationship is linear. Thankfully, this assumption is very easy to test for. Everybody kind of agrees on its solution, and so it's not a big deal. The second one I've already discussed, this idea of no measurement error in our predictor variables. The third one is homoscedasticity, and we'll talk more about this in a few minutes, but overall, conceptually, this just means that across all values of our predictor, the variability of residuals around those predicted values will be equal. Okay, so the dispersion of residuals around the line will be equal at all levels of the predictor. Residuals will be independent and uncorrelated. Thankfully, this one is easy to test for and it's easy to resolve as well due to new data techniques like multi-level modeling. So very thankful for that. Sometimes data is analyzed by groups. So for example, we could have nested data where we have teams and organizations, and a lot of times the members of the same team share different attributes with one another, more so than they share those attributes with members of a different team. So when we have individuals nested within teams or individuals nested within departments in an organization, that is an example of nested data. And nested data often contains correlated errors. Let's say we measure the same individual across time on the same variable, and because we're looking for changes over time. That person would have correlated errors because it's the same individual over time. And so regular OLS regression doesn't work well for time series types of designs, longitudinal designs, and also for nested data, where again we have people nested within teams or groups. So in that case, we would not want to do a regular OLS regression that we're learning in this course. We would want to use a repeated measures ANOVA, or even better, a multi-level modeling technique, or MLM, where we are accounting for the similarities within the group. We're accounting for shared variant, people having shared attributes inside groups, more so than they'd share with people outside their group. So more on that next quarter. You'll learn all about MLM later. But for now, just know that it is an assumption of OLS regression that our residuals be independent or uncorrelated. And finally, residuals are normally distributed. This is another assumption of regression. And if we have categorical data, such as male-female or ethnicity, maybe we have classrooms in an education setting, we would want that outcome to be normally distributed within those categories. And so this is analogous to the Levine's test for an ANOVA. So it's very similar. We have kind of the same patterns as you can see popping up through statistics. We can see similar patterns as we move along. So these are the assumptions of regression. Please know these 5 assumptions, and I will show you how to test for and deal with each one in turn in the upcoming sections.